All right, here we're on chapter 4, analyzing change, and we're looking at applications of derivatives. So section 4.4 here is about inflection points and second derivatives. So a point at which a graph changes concavity is an inflection point. So if you remember, when we're coming up here, then it comes up here, we go like that. That point right here, or roughly right there, that's going to be our point of inflection. Now it's going to be the point of greatest or least slope. It's going to be greatest for positive. If it's coming down, it'll be the least slope in a region around that inflection point. So it's getting bigger and bigger, and then at that point it's the max. Then it starts getting smaller and smaller and smaller here. So our tangent lines, get to be the biggest, and the biggest tangent is right there, and then they start getting smaller as we go. Now, for continuous function f that has differentiable rate of change function f prime, or the first derivative, the input c of an inflection point on the function can be found by locating the input c at which f prime has a relative extreme point. So what's going to happen on here is this might look something like that. So that's going to give us that relative max. Now they're not lined up perfectly, but that's what would happen. That inflection point is going to be found by finding what that max is. And that's what we did at the beginning of the class, where we had to find the inflection points. We took the derivative and we found either the max, or if it was coming down, then we would find the min, and it would be, down, and that would be the point where that inflection point was for the x-axis. Okay. Now, when f prime, or the first derivative, is now it's the rate of change. Okay, so it's not when, it is the rate of change of a function of f, and then that derivative of f prime, that is, if we take the derivative of the derivative, that's called the second derivative of f, and it's denoted f double prime. So, we have our function, then we can take the first derivative, and then we can take our second derivative. Okay. Now, what that does is it helps us move through a process, and be able to solve things differently than what we've done up to this point. Now, note that the second derivative represents the rate of change of the first derivative, and the unit of measure is going to be the measure for the output of f is going to be, like, if this was, hours, and this was hours per week, then this is going to be hours per week per week. Okay. All right, so that's going to be how it is. So it's going to be the unit of measure for the output of f prime, which is the hours per week, divided by the unit of measure for the input. So, that's how it's going to look like. Now, another way we can write that instead of f double prime is we can say d squared f over dx squared. And if we don't want to write it with the f up here, we can, d squared over dx squared of f of x. Okay, and so that's a second way to write it. All right, so the point where a function f of x is increasing most rapidly, kind of like we told you before, is the inflection point. And that occurs where f prime is at a max. Okay, and so, that's either going to be the max going up or the max going down. Either it's the max or the min, kind of how you think about that. Now, this point occurs where f double prime, the second derivative, or the derivative of f prime, is 0. All right, so what happens is, when we have, this is, our inner, well, it's not very good. So that's going to be our point of inflection, and when we get that, it's going to give us this here as the f prime. So that's f prime, and so now we don't really want this going down as well. And so when we take a derivative of this, that's horizontal, and so it's going to cross at that point, and so it's kind of be, your tangents are positive and then they're negative, so it's going to kind of go up, kind of like that. It's probably going to be, if that's a quadratic, it'll be a straight line, or however it is. It's going to depend on what your curves are, how that is. And so what we're going to do is we're going to find f prime and f double prime, or the first and second derivatives, and once we find our second derivative, the f double prime, we're going to set that equal to 0 and solve for x. Now, if we use our calculator, the numerical solver, and it comes out and says there's no sign change, what happens is there's no inflection point existing. Okay. Now, that happens sometimes, and that's not a big deal. It just means there's no inflection point, and so we don't have this set equal to 0. But if we do, we can use the x values and plug them back into f of x, and we get our inflection points, which is the highest rate of change. And we also can plug them back into f prime, or the first derivative of x, to find the rate of change. So we can find inflection points and our rate of change once we do find that x value from the second derivative, setting that equal to 0. Okay. Now, there's this thing called the point of diminishing returns. I'm sure you've heard it in some manner, no matter what area you're in. And basically, in some applications, the inflection point can be regarded as that point of diminishing returns. It's the point after which each additional unit of input results in smaller gains in output. Okay. And so, to qualify as a point of diminishing returns, that inflection point must appear on an increasing function that's concave down to the right of the inflection point. And so, that's kind of like the kinds I've been drawing. We're going like that. So we're increasing, we have that inflection point, and then it just doesn't keep going as high as quick as it used to. It's starting to slow down with each additional input up. It's not getting any gain here for higher x values. Okay. Now, there's an interesting note. The point of diminishing returns on the retention rate function is one factor that led many educators and counselors to suggest studying in 2-hour increments with 10 to 15-minute breaks between them because of that diminishing returns. Studying longer is not going to help. You get smaller and smaller gains the longer you study. And so it's better to, do that 2-hour block and then take some break and then come back again. Now, concavity and the second derivative. Well, because the derivative of a function is the slope of the graph of that function. Now, if we think about that, we're taking the slope graph of the original function to get our derivative graph, which is also called the slope graph. And a positive derivative indicates the function output is increasing, and a negative derivative indicates that the function output is decreasing. Now, the second derivative provides similar information about where a function graph is concave up and where it is concave down. And so basically, we have words here, but if the second derivative is greater than 0, then the derivative is increasing and the function itself is concave up. Now, these words put into saying is the second derivative of x is less than 0, then we have the first derivative is decreasing and our function is concave down. And then if the second derivative changes from positive to negative, so if you're drawing your graph and you have your axes and it kind of does something like this, it goes from the negative to positive or positive to negative if it's going the other direction. At a point P on a continuous function f, then P is an inflection point. So once we find that point there, that's going to be an inflection point on our original graph. Okay. And that's our 0 point that we're looking for when we set the second derivative equal to 0. All right, so here are some graphs to kind of represent some different things. We have our function, we have our derivative, and we have our second derivative, okay? And so what it shows is our second derivative is positive for, for that whole 0 to 5 interval, okay? And because of that, our first derivative is increasing over that whole interval as well, okay? So it's increasing over the whole interval. And our function, original one, is concave up and has a relative minimum. And if we think about where that relative minimum is going to be, it's going to be where we have the horizontal point, and that's going to be where our derivative here crosses the x-axis. And so this point here, where we find that slope of that tangent there, that gives us that point there. And so we know that's going to be our minimum value. All right, so our second derivative test for relative extremis. So suppose we have a function f, it's continuous over an interval that contains c, so you have to have c somewhere in that interval. If the first derivative is equal to 0 and the second derivative is greater than 0, then f has a relative minimum at c. Okay, so if we look at this and we have some interval and we're going maybe from here to here, then this one is positive, this one is increasing, and so we have some minimum value. Now if we go the other way, it's going to be the same thing. So if f or the first derivative of c is equal to 0 and our second derivative is less than 0, then f has a relative maximum at that c. Okay, so that's kind of a key thing to think about. Here what we're seeing is it's kind of a just a different interpretation of graphs. So here we have our function, our second derivative, and our first derivative. And so here we're seeing that we're going to have some kind of shape that's different. We have these kind of shapes all over, and what we're going to see is the second derivative g prime has a 0 near 1.8, and so that's going to be where it crosses that axis. So well, what does that tell us? That's going to be equal to our point of inflection right there. Okay, so that's the point of inflection on our original function. And it's also going to be the max value of the derivative. Okay, so since it's going from positive to negative, then it's going to be the max. And so we're going to have that. And so we'll see uh, that being a max value. And so it's an inflection point. It's the max value for our derivative. And so that's the rate of change is at the max point at right there. And so that second derivative really does help us find different things on the two graphs of g and g prime, or the first derivative. Now this kind of lines it all up kind of nicely in three graphs, top to bottom, function, derivative, second derivative. And so if we think about this, what happens? Well, we could draw all these horizontal lines, which are going to give us a slope of 0. And if we see that, well, guess what? We have a slope of 0. And here we have a slope of 0. Now this one, that one's going to give us horizontal too, because the way it's drawn, that's going to give us a horizontal tangent through that, and that's the point of inflection. But still, it's going to give us that 0 point there for the slope being 0. Now what else? Well, here we're going to have a point of inflections. Okay, so that point of inflection is going to give us, in this case, a max, because we're on an increasing slope. And it's also going to be a point where we have a 0 for our second derivative. Okay, now we can come over here and we see another point of inflection. And if we see that, that's another max because it's positive. And we have another 0. So we would expect that. Now this point of inflection, well, that gives us our 0, which we'd expect, and it also is going to be a 0 here. And that's because that one's just a flat one. It's not increasing, it's not decreasing, it's 0 for our point of inflection on that one. Okay, so it kind of does multiple things. It's point of inflection, you have a horizontal uh, um, tangent, and so you've got multiple things going on there. So that's kind of how we can use each of the curves to figure out what the other curve is going to look like. Okay, and what we'll do eventually in homework is they'll give us 3 of these scrambled up, and we're going to have to decide which one's a function, which one's the derivative, and which one's a second derivative. All right, so at that point of inflection on the graph of a function, the second derivative is either going to be 0 or it's not going to exist. Now, if the second derivative of the graph is negative on one side of an input value and positive on the other side of an input value, then we have some kind of inflection point of the function occurring at that value. And so here's our second derivative. One side we're positive, the other side we're negative, and so that means there's going to be a point of inflection at C, and we can see that our original graph, we did have that point of inflection. It's going from up and then down, and so that would be our case there. All right, so let's stop there. We'll start some examples in a little bit.